Hello, ladies and gentlemen. This is Mr. Hunter, and this is your Light Notes Part 1. This is the second part of the waves unit. So in the first part, I've taught you about the basic characteristics of a wave, as well as different effects, and we talked about sound waves. And then all the different things that sound waves can do, like Doppler effect and resonance, and uh, how amplitude and frequency affect pitch and how loud it is. So now we're going to actually talk about light. Now, I studied light in college, and it's really, really cool because light has four different natures in and of itself all at the same time. And depending on how you observe it, you can see that nature. So let's start out with the ray model. The ray model is light travels as a straight line. And you see this all the time, like when you look outside and you're looking through the clouds and you can see the sun rays. You see light acting like a straight line. Or when you look down and you can see your shadow's formed by mostly straight lines. So, and then if you have a laser, which is light amplification through stimulated emitted irradiation, if you have a laser, that's a perfect model of light acting as a straight line. Now, light also acts like a wave at the exact same time that it's acting as a straight line. However, there's different ways we can look at it to make the wave nature and the wave property come out. And the wave is actually, remember from your reference table on page 2, it's called the electromagnetic spectrum. The wave model light is exactly that. It's electromagnetic because the green wave is magnetic and it travels 90 degrees at the exact same time to the electric wave, which is the red wave that I drew on here. And I tried to draw them on 90 degrees, but it's kind of hard to do on a two-dimensional board to draw something 3D. So with relative to each other. So what ends up happening as this wave propagates, and remember as I showed you in class with the slinkies, is I have a wave that's going left to right, and at the exact same time, I have a wave that's going up and down. And this is the electric and the magnetic part of the wave of light. And then we have the particle model of light, which we won't speak of too much here, because we really deal with it when we deal with modern physics next unit, but it's called the photon. The photon's a ball of energy. And just like the electron, remember the electron can only exist at specific values, the photon can only exist at specific values. And those specific values relate to the objects, or the light, excuse me, its frequency. Because like I can get a violet photon or an ultraviolet photon, or I can emit a red photon, and that will be a certain frequency of like 650 nanometers if it was red. So we'll get into more into that next unit, but I just want to introduce it here because it is one of the models of light. Then we have quantum, which is like the quantum model deals with how light operates on a very, very, very small scale, but we won't deal with that in here. Get off my board. No, I'm not interested. Get off. No, get. Sorry, ladies and gentlemen. Okay, so the first thing I want to talk about is reflection. So reflection is a property of light, and I want to go right down to the definition. The definition of reflection of light is simply bouncing off of a surface. And it follows this law of reflection. And the law of reflection states that the angle of incidence, or the incoming angle, equals the reflected angle, or the angle of reflection, excuse me, which is the outgoing angle. And that is always true no matter what type of surface. The easiest example I could use is you use this in pool. You use this in pool when you bank a ball off of the side, or you even use it when you're hitting other balls at an angle with the cue ball. Now, here's the critical thing. Make sure you draw this picture down, because this is really, really important. So the black line that you see that I drew, that I'm moving right now, is the surface. And the dotted line that I drew is called the normal. And if you remember force normal, it's the force perpendicular to the surface. When we are determining angles, we always measure an angle next to the normal, or with respect to the normal. So when I measure this angle, or my incoming angle, I measure it between the incoming ray and the normal. I never really measure it with respect to the surface of the material. So that's why I put in blue quotation marks, always measure the angle from the normal. So always measure that with respect to the normal, and also the outgoing angle. The outgoing angle is always measured with respect to the normal. So if you notice here, I said, okay, the incoming angle is 15, and it's bouncing off a mirrored surface. So the outgoing angle, or the reflected ray, is also 15 degrees. And so my angle of incidence equals my angle of reflection, and it's always measured relative to the normal, and you got to remember normal is 90 degrees from the surface. That is super important because it also deals with what we're going to talk about next, which is refraction. Refraction is when light bends because it enters a new material or medium. Now, remember what we talked about with a wave and a sound. The only way to change the speed of a wave is to change the medium that it's in. Well, we're finally changing the medium, ladies and gentlemen. We're now going from one material into another. And since we're doing that, the speed will change. The fastest we know that speed can travel is 3 times 10 to the 8th meters per second in a vacuum, which is written right there, and which means that it can only go slower than that. Light cannot go faster than that speed. So in air, it's 1.003 of an index, so it travels technically like 2.98 times 10 to the 8th meters per second. So think about it like this way, like I said in class. If you're running on the side of the pool, you're running through air, right? And you can go pretty fast. But let's say now you jump into the water and you try to run through the water, you can't run as fast. And as a result, that means that my velocity goes down because I can't run as fast. And so my velocity goes down, the other parts of that equation have to change. Now, here's the thing. When I shine a red light into water, it's still red. When I shine a green laser into water, it's still green. So that means that the frequency of the light does not change. Since the frequency of the light does not change and stays the same, since my speed went down, my wavelength also has to go down to keep that equation balanced. Like if velocity is 10, and frequency is 5, well, wavelength now has to be 2 because it has to balance the equation. So by now you should have also hopefully drawn this picture. So here I have the incoming light coming from air, which is index of 1.0 essentially, into water. Now notice that I measured my angle with reference between the ray and the normal. And now it gets refracted into the water and it bends towards the normal. So that's my index, or that's my angle of refraction. Now, I've been throwing this word index around. Well, what does it mean? The index of refraction is the ratio of the speed of light in a vacuum versus the speed of light in the material. So we call C 3 times 10 to the 8th meters per second, which is the speed of light in a vacuum. So the index of refraction of a material is just a measure of how fast light is in a vacuum versus how fast light is in the medium. And so that gives us that end value. The higher it is, the lower or the slower the light will be in that material. Now we have Snell's law. And like I said, this is the most math you'll probably end up doing in this unit. And Snell's law just says the index of the first material times the sine of the angle that the light is coming in at equals the index of the second material times the sine of the angle that it refracts at. And so that's Snell's law. And using that, we could say, okay, if I know both my indices and I know my incoming angle, I can figure out my outgoing angle. Or if I know both my angles and I know my incoming index, I can figure out my second index. So that's what that equation is, and we'll practice that in class a bunch. Now, here's a little hint I want to teach you so that you here's a little hint that I want to teach you so that it's a good reference point so you could figure out if you're doing the math right. So if light goes from a lower index to a higher index, it bends towards the normal, aka the angle gets smaller. Actually, I didn't write that early in class. I'll write that here. So angle gets smaller if you're going from a lower index to a higher index, and vice versa. The angle will get bigger if you're going from a higher to a lower. So that's like just a really good way to analyze what's going on. So if you're given a problem and you see that the light bends away from the normal, you know it's going into a lower index. Or if it bends towards the normal, you know it's going into a higher index. So that is your light notes part one. The only thing that I forgot is I forgot to add that polychromatic means poly is many colors. And remember when we looked through the diffraction gratings, we saw that when we were looking through the diffraction grating, we saw that white light actually consisted of all the colors. It was polychromatic. And monochromatic is just a laser, and that just means one color. So that's your light notes part one. I will be looking at this and checking it when you bring it into class. Have a good one.